Mr. Eric, Mr. Ryan, are you right?
Yeah.
Okay, so remember what we talked about yesterday? The rod, yeah, the rod. We want to cut the rod, yeah, and we want to sell the rod, right? So 1, 3, 5, 7, 7, 7. Okay, so that's the rod. If we can sell the rod, cut the rod, and we can sell the rod. If it's size 1 is, for size 1 we get $1. For size 2 we get $3. Size 3 we get $5, etc. Okay, if we have a rod with size 6, and the maximum profit we can get is cutting into 2 pieces of 3, then we get $10. Or you can cut it with what? With 2 and 4 and still get $10. Okay? Yeah? This is actually a unbounded knapsack problem. What's knapsack? What's knapsack? What's knapsack? Anybody?
Knapsack is a not very.
Knapsack. Okay? Knapsack. It's a bag. Yeah? It's this bag. Look. Knapsack. Okay? Look. Okay? So unbounded knapsack. What does it mean? It means that we have a few items. Yeah? Yeah, this is the item we have. We have items. This is the item value. Okay, let's say the value of the items. Values of items. And then the size for it is for each one is 1, 2, 3, 4, 5, 6. This is the size for that. This is the value for that. And we have a knapsack which has capacity with n. And for each item you can choose as many as you want, as long as the total weight does not exceed the total capacity. Okay, and then we want to maximize the value, right? We call it unbounded knapsack. Unbounded. Okay, so look, we want to maximize what? We want to maximize the profit, which is what? So for these items, yeah, we can pick as many items as we want, right? So let's say if for each one we pick what number, the lowercase ni, okay? So we want to pick p equals ni times its values vi, yeah, yeah, we get the sum as long as what? As long as as long as its total capacity does not is less or equal than n, right? So the total capacity is what? Ni. Okay, that's the weight. Okay, let's say the weight I. Okay, yeah. As long as the total capacity Ni times Wi, right? Yeah, Wi is less or equal than total capacity is bigger n. Okay. And because Wi equals I plus 1, right? I plus 1. If I start from 0, so we can change this to I plus 1. Okay? Yeah? This is the knapsack, unbounded knapsack. And yesterday we used the what? What kind of approach did we use yesterday?
We use depth search.
Depth search. We use the cache. So eventually you make it what?
Top down.
Top-down dynamic programming. Okay, so let's review this a little bit. Cache, yeah. What's cache? Caching is asking computer to memorize the values for us. Okay, yeah. So this is the magic keyword. Okay, so we are asking computer to memorize. Yeah, because if you don't ask computer to memorize, he just forget. And next time you ask it to calculate it, what happened? He forgets. He calculates again. It takes time, right? But if we adding this cache, okay, then if DFS3. It calculates it. For example, it spends like 10 minutes to calculate it, right? Yeah? And then he remember it. He remember in his memory, yeah? His memory, yeah? And the next time, like 5 minutes later, I asked computer, what's DFS3? Does it need to calculate again? No, you just immediately fetch it from the cache, yeah? From the cache. What's cache? What is the meaning of the cache?
Remembering.
Okay, remember. It's associated with remembering. So what's cache thing? It's like a memory thing. You know the cache, yeah?
Money.
Not that cache. Not this cache. Cache. C-A-C-H-E. Cache. What's this in English?
though.
Caching is
That
like,
looks like another language to me.
yeah, caching is like computer cache, memory. You can treat it as a memory, right? And it's exactly the purpose of this. I cache it. I cache it for later uses, okay? So n, like I try for, look, if the size is n, and I can cut it in n ways, right? For each way, I cut it. If cut it, I keep the size with I, right? Keep the size with I plus 1 actually. And the profit on keeping that is price I. And the remaining size is n minus I minus 1. And I could recursively calling the deficit function. Right? And then we want to calculate the, what? We want to calculate the maximize, yeah? So it's the maximum profit. Okay, so why I write the minimum here? This is the maximum, right? This is the maximum, yeah? We want to get the maximum, okay, not the minimum, okay? That was a mistake, okay?
Mistake, please.
Yep.
Don't you put it there as well?
So now, so what's bottom up, right? So top down, let the computer to cache it for us. The bottom up, we need to remember the things ourselves and using the static array. So we remember the values in the array, okay?
In DP.
Yeah, DP array, okay? So let's write it. So we want to be able to cache is the to be able to store n values for dpn, right? So let's say, so look, for previously this dfsn array yn, make noise again. We have n values. So now we just have a dp array which is at the beginning at 0 times n plus 1, okay? So we are storing the values in this dp array, right? Ari, what did that just say?
Storing stuff in the DP array.
Okay. Then I can go through the values I want to check. I want to calculate, which is n plus 1, and then I need to go through the values up to range I. Yeah. And then dp I equals the minimum of dp I, and then yn. So look, I want to calculate the dp I value. This is corresponding to previously dfsn, right? Okay. I want to calculate the dp I value. I want to get a maximum. So how I can cut it in j ways, yeah? In j ways. So I can cut it as dp. So now the remaining is what? I minus j minus 1, right? Yeah. This is the remaining size plus price. This is the value, the value, yeah? The value we can get by keeping the size what? Keeping the size what? J, right? Size j plus 1, right? Because it starts with 0, j plus 1, right? And then return, we just return the dp n, right? Or we can return dp minus 1, right? Easy. You see? That makes sense. And so,
I got a question.
yeah, that's a good question.
On the fourth line, you said it would be the maximum, but you've written minimum.
Good job. Yeah.
That's a comment.
Yeah. I always write a mistake. Okay, it's maximum. What did they say? I said maximum or minimum?
You said maximum.
But I wrote the minimum. Yeah.
Yeah.
It proves you actually listen. That's good, right? You're actually listening. Yeah. You pay attention, right? Got it? Yeah. Because sometimes I write the code, I write mistake. But when I say something, I wrote it. I may not write it correctly. Okay. Okay, what's the time complexity if you're looking at this? What's the time complexity? What's the time complexity for this one?
Oh, n.
That's one loop.
2n.
That's another loop.
n square.
Yeah, n squared. Look, this I goes to n, that n iteration. But for each I, it needs to go to j, right? So actually it's, look, n plus n minus 1 plus n minus 2 plus okay? So these, if you add it together, it will be something like n plus 1, you know, yeah, if you add it to 1, then it will be n plus 1 divided by 2, okay?
That's a
n plus n minus 1 plus n minus 2 plus tier 1. Do you recognize this?
Yeah,
1 plus 2 plus 3 plus 4 plus 5. The equation is this. This is not Fibonacci. Look, 1 plus 2 plus 3 plus 4, 5, yeah? past till 100, what's the sum?
50%.
Yeah, 50-50. If 100 times 100 plus 1 divided by 2, 550 times 101. What's this?
50-50.
Yeah, exactly. So that's the equation, yeah, to sum up the first n integers from 1, okay? So look, this one, if we wrote it out, it will be n squared plus n divided by 2. First of all, we drop the constant. Second of all, look, this is n squared. I have an n here, but look, which is bigger, n squared and n? Which is bigger? If n bigger than 1?
N.
Which is bigger?
N squared.
N squared, yeah. So in n squared, this is bigger. So when we say complexity, we always keep the most dominant one, right? Because this is much more complicated than this one, so we also drop it, okay? It makes sense? Yeah, we talked about this before. So that time let's say O(n) squared. That's why we get the O(n) squared, okay? Yeah. Because look, the second iteration does not go to the n, right? It goes to the I only, right? If this it goes to n, for each I, for each n, another n, so that's n squared. That's easy, right? We can easily get O(n) squared. But for this one, I goes to n, for each j goes to I. So that's what we get. So let's the complexity is actually O(n) squared plus n divided by 2. First of all, we drop the constant. Second of all, we drop the smaller part. So we keep this most dominant part, which is O(n) squared. That's why we get it. Yeah? Space complexity. What's here? Look at me.
OGP, O1.
N.
O(n), yeah, because we are allocating n, right? And as for
ON plus 1.
okay, O(n) plus 1 is actually O(n), okay? We drop the constant. We don't talk about the constant in the time or space complexity, okay? Yeah? Make sense? Look at this one. What's this? What's this? We want to calculate dpi. First iteration, we want to calculate the dpi, right? dpi. And then for each size of I can cut it into, remember the previous one, the top-down dynamic programming, we go through the ways of cutting the rod, right? So if now I
So it's
keep the,
ON plus.
no. If I keep the size with j plus 1, and the remaining size is I minus j minus 1. Remember I asked you this question, yeah? The remaining. So this is the remaining one. Previously we using the recursion with the cache to ask computer to do it, to look it up the values we calculated before. Now we look it up in a stationary in an array, right? Because we are memory. You know, we remember those things, those values using an array by ourselves, right? Proactively remembering the values. And this is the profit. Price J. Can anybody explain to me what's this bit? Price J.
Price J is the
Yeah?
J.
Yeah? That's the size, yeah?
J is the size thing, and the price is the price for each size.
Yeah, the value, yeah, the value we can get, yeah? So look, let's roll, yeah? If I cut it with this is the bit I can sell for the money, yeah? And then remaining, I don't know how many clocks, right? I look it up here, okay? I look it up. This bit I cut it with J, and the value I can get is here. And I want to get the maximum, okay? Make sense? Yeah, that's it for today. Good job. Bye bye.